In this video, I will discuss the process of making X-rays and modulating X-ray production. The control panel of an X-ray unit allows you to set parameters to modulate X-ray production. In this video, we will discuss the parameters that influence the quantity and quality of X-ray photons and why you should modulate them in order to make good radiographic images. You should be familiar with the components of an X-ray tube and the process by which electrons are generated and accelerated towards the anode to make X-rays. Next, let's discuss what happens when the electrons collide against the tungsten target. Most of the electron's kinetic energy is converted into heat, and less than 1% is converted into X-ray photons. Bremsstrahlung photons are the primary source of radiation from an X-ray tube. Derived from the German word Bremsstrahlung, which means breaking, these photons are produced when the electrons are slowed down or stopped by the tungsten target nuclei. Most often, the electrons are deviated from their path by the positive charge of the nucleus. The energy loss from the deviation is emitted as an X-ray photon. Occasionally, the electron may directly collide with the nucleus, losing all of its energy, which is converted into an X-ray photon. Bremsstrahlung interactions produce X-ray photons with a continuous spectrum of energy. This reflects the differences in the energies of the incident electrons as well as differences in the deflections of individual electrons. Now let's graphically evaluate Bremsstrahlung radiation production. On the x-axis is photon energy in kiloelectron volts, and on the y-axis is the number of photons. Note that Bremsstrahlung radiation produces photons with a spectrum of energies, both low and high energy. Characteristic radiation contributes to only a small fraction of the total radiation output. Characteristic radiation occurs when an incident electron interacts with an electron from an inner orbital, causing it to be ejected from its orbital. The vacancy created is filled in by an electron from an outer orbital. The difference in the binding energy between the two orbitals is emitted as an X-ray photon. The energies of the characteristic photons are discrete because they represent the difference of the energy levels of the specific electron orbitals and thus are characteristic of the target atoms. The production of characteristic radiation has no practical implications for dentomaxillofacial radiography. So, to summarize, most output of the X-ray tube is Bremsstrahlung radiation, which has a continuous spectrum of energies. Note that the Bremsstrahlung radiation has a peak energy, and this is set by the operator prior to imaging. Also note that the mean energy of the beam is substantially lower than this peak energy. There are practical applications to Bremsstrahlung radiation. Practically, we do not need all of the X-ray photons that are produced to make our radiographic images. We really need the photons that are in the middle energy range, and the photons that are at the lower energy range and at the higher energy range do not contribute substantially to our image formation. Next, let's look at modulating X-ray production. There are three principal controls for an X-ray tube: the peak kilovoltage, the milliamperage, and the exposure time. Let's start with the exposure time. The longer the exposure time, the longer the filament is heated, and it produces more electrons and thus more photons. When you double the exposure time, you double the number of photons that are produced. Note that in this graph, the difference between the 1 and the 2-second exposure is purely the numbers of photons. The peak energy and the mean energy of the photons remains the same. Thus, increasing or decreasing the exposure time will increase or decrease the number of photons but does not impact the energy of those individual photons. Next is the milliamperage. The milliamperage is a reflection of the heating of the filament, the current used to heat the filament. A higher MA results in more heating of the filament, producing more electrons and more photons. When you double the MA, you double the number of photons. Note that when you change the MA, you do not change the peak energy or the mean energy of the beam. Also note that the effects of changing milliamperage and seconds are essentially the same. For this reason, exposure settings for milliamperage and seconds are often considered together as a product of milliamperage and seconds. Thus, a 0.1 second exposure with 10 MA produces the same number of photons as a 0.2 second exposure with 5 MA. From a practical point, it is advantageous to keep the MA higher and the exposure time lower so that we can minimize the chances of patient motion during imaging. The next parameter is the kilovolt peak, which reflects the potential difference between the anode and the cathode. Increasing the kVp increases the potential difference between the cathode and the anode, increasing the kinetic energy of the electrons as they move towards the target. The greater the energy of the electron, the greater the probability it will be converted into an X-ray photon at the target. Note that when you increase the kVp, you increase the number of photons generated, the mean energy of the photons, and the maximal energy of the photons. Thus, changing the kVp changes both the quantity of photons as well as the quality or energy of the photons. To summarize, milliamperage and seconds have similar effects on X-ray production. Increasing the MA or increasing the exposure time will increase the number of photons. In contrast, increasing the kVp will increase the maximum energy of the photons, the mean energy of the photons, as well as the photon number. So what is the practical application of this information? In order to make a good radiographic image, we have to have photons that penetrate through our patient and reach a receptor, where they will record a radiographic image. There are differences between the imaging systems, and this requires that dentists optimize the imaging system used in their clinic. Additionally, we also need to customize exposure for individual patients. This takes into account the patient's size and the anatomic region being examined, and accordingly we will vary the milliamperage, seconds, or sometimes the kilovoltage. In subsequent modules, we will discuss details of making good radiographic images.